In January 1998, a stationary weather front over the St. Lawrence Valley produced freezing rain for more than 80 consecutive hours. Ice accumulated on transmission towers at rates that exceeded engineering tolerances. High-voltage lines carrying power across northern New York and Quebec began to fail under radial ice loads approaching 2 inches in diameter. The regional grid entered cascade failure. The North American power grid in 1998 used lattice steel towers to suspend high-voltage transmission lines across rural corridors. Design standards assumed ice accumulation of 1/2-inch radial thickness with concurrent wind loads. Towers were spaced at intervals of 800 to 1,200 feet. The grid operated in a triangulated configuration. Power from hydroelectric facilities in Quebec moves south through corridor lines rated at 735 kilovolts and 315 kilovolts. Local distribution used wooden poles rated for loads under 25 kilovolts. The system had no provision for shedding ice during prolonged freezing rain events. A low-pressure system stalled over the eastern Great Lakes on January 4, 1998. Warm, moist air from the Gulf of Mexico moved northeast and overran a shallow Arctic air mass trapped in the St. Lawrence Valley. Surface temperatures remained between 23 and 28 degrees Fahrenheit. The air mass at 3,000 feet measured 38 degrees. Precipitation fell as rain through the warm layer and froze on contact with surface structures. The front remained stationary for 5 days. Meteorological models did not predict the duration of the event. Freezing rain began across northern New York at 0400 hours on January 5. Initial accumulation rates measured 0.1 inches per hour. Utility operators recorded ice on conductors but observed no immediate structural concern. By January 6, radial ice thickness on transmission lines exceeded 1 inch. The weight per linear foot of conductor increased from 2 pounds to over 12 pounds. Wooden distribution poles began to lean under asymmetric loading. The first high-voltage tower failure occurred near Messina, New York at 1930 hours on January 7. Precipitation continued without interruption.
The freezing rain event persisted for 80 hours. Total ice accumulation on exposed surfaces reached 3 inches radial thickness in some locations. A single span of transmission line between towers accumulated over 10 tons of ice. Conductors sagged below minimum ground clearance. Trees weighted with ice fell across secondary distribution lines. The mechanical load exceeded the yield strength of both steel lattice members and wooden pole fixtures. Towers designed for vertical loads experienced bending moments that induced buckling at welded joints. Failure propagated along transmission corridors as adjacent towers absorbed redistributed tension loads. The 735 kilovolt transmission lines from Quebec to New York operated in a 3-wired delta configuration suspended from steel towers exceeding 100 feet in height. On January 8, a tower near the Canadian border collapsed under ice load. The failure transferred mechanical tension to the 2 adjacent towers. Both structures buckled within 15 minutes. The cascade extended along 12 miles of corridor. Similar failures occurred on parallel 315 kilovolt lines. By January 9, over 130 transmission towers had collapsed in the North Country region. The triangulated grid lost structural integrity. Power could no longer move from generation sources to load centers. Loss of grid power disabled electric heating systems in agricultural facilities across northern New York. Dairy operations dependent on milking machines and refrigeration lost operational capacity. Water treatment plants relying on electric pumps ceased distribution. Residential wells using submersible pumps provided no water. Wastewater lift stations failed. The coupling between the electrical grid and secondary infrastructure became evident. Backup generators required fuel deliveries that could not occur due to road obstructions. Hospitals operating on emergency power exhausted diesel reserves within 48 hours. The failure was not confined to the electrical domain.
Fallen transmission towers and ice-loaded trees obstructed over 2,000 miles of roadway in the North Country. Steel lattice structures weighing multiple tons blocked 2-lane highways. Removal required cranes and cutting equipment. Road crews could not access obstructed segments due to prior obstructions. The transportation network entered gridlock. Utility repair vehicles could not reach failed infrastructure. Fuel tankers could not deliver diesel to generation sites. The physical geography of the region compounded the blockage. Single road access to rural communities became impassable.
Helicopter insertion of repair crews was limited by weather and landing zones. Restoration of the transmission grid required replacement of collapsed towers and restringing of conductors across spans exceeding half a mile. Equipment to perform this work included boom trucks, tensioners, and helicopters. Frozen ground prevented the use of outriggers and stabilizers. Ice on unpaved access roads made movement of vehicles over 20 tons impossible. Replacement towers were transported from fabrication facilities in the Midwest. Delivery required clearing of the road network. The work sequence could not begin until the roadways were opened. Roadway clearing could not proceed until heavy equipment arrived. The loop had no entry point. The January 1998 ice storm resulted in the failure of 130 high-voltage transmission towers, over 30,000 wooden distribution poles, and more than 1,000 steel distribution poles. Approximately 16,000 miles of distribution line and 1,300 miles of transmission line required repair or replacement. Peak outages affected 4.7 million customers. Total customer outage hours exceeded 100 million. Some rural customers remained without power for 33 days. Economic losses in New York and New England were estimated at $3 billion. The event exceeded the design envelope for cold region electrical infrastructure. The Federal Emergency Management Agency issued detailed reports on the ice storm in 1998 and 1999. The North American Electric Reliability Corporation revised standards for ice loading on transmission structures. New design criteria specified radial ice thickness of 1.5 inches with concurrent wind. Utilities in the Northeast began programs to reinforce or replace wooden poles with steel or concrete. The National Weather Service improved forecasting models for freezing rain duration. The 1998 event became the reference case for infrastructure resilience studies. No subsequent ice storm in the region has matched the 80-hour duration or the extent of structural failure.